Well, hello everyone, and welcome to the live stream. I'm Nathan, and I'm here with the co-host.
I'm Anvita, and we are all very excited for the upcoming launch.
Yeah. So, yeah,
First, we have some updates about what's happening at the launchpad. So, the first launch window is just about to open, which means that the launchpad is not yet accessible, but we are going to be getting there very soon.
yes. So in the meantime, we can show you some videos of the tests that we've done and some interviews that we've held. Yeah.
So that you can get the background on what's going on and what it took to put the rocket to the launchpad.
Right. So yeah. Um, what we should start with?
Let's start with the interviews, I think.
Okay. Let's pull up some interviews.
Hi, could you introduce yourself?
Of course, I'm Alan. I was the head of avionics for year 2 in Stratos 5, and I've continued through year 1, 2, and 3 as an electronics engineer working on some of the electronics within the rocket.
Yeah, and what kind of electronics did you work?
So I was mainly focused on the avionics, that's the small PCBs and wiring within the rocket itself. There are other people who worked on ground systems and support infrastructure, which are arguably more important than what's actually contained within the rocket itself. But that was my little domain.
And you said avionics, right? What does avionics exactly do for the people that are not technical?
So avionics is a portmanteau of aviation electronics. So it just means any of the electronics that are involved in making something fly. So that's any of the sensors to detect. So your barometers, your GPS sensors, your attitude detection, your telemetry systems, all of those. Anything that makes the rocket work.
Okay. And what was the biggest challenge for you this year? Or any year you worked on Stratos?
The biggest challenge has always been just the pure scope, because Stratos 5 is by far the most complex project we've ever worked on in DARE, and electronics is required for every single step in the process. You can't just rely with analog systems, you can't just have someone hammer a wrench in place, you need to have electronics to control everything. And the overall complexity of the project itself has been the most difficult thing the whole time.
That's interesting. And how does your system connect them with the rest of the rocket? What does it exactly do?
So, electronics connects with the whole system because it connects to everything. It connects with every single sensor, it connects with every single valve that controls the propulsion system, it connects with the batteries that power the rocket, it connects with all of our live data input, it connects with our testing setups, it connects everywhere. Every single element behind the rocket, whether it's propulsion, recovery, or even structures related, electronics is embedded in some way. That's just how we control the rocket. We don't have expendable minions that can go up and just twiddle knobs for us.
Okay. And what was then for you the most exciting moment in Stratos?
So the most exciting moment was when we had our first successful test campaign using the engine control unit. Because that was a fully integrated stack of PCBs that were designed by a number of people that I had a nice hand in, and it was all done with reasonably cheap electronics that we put together and soldered by hand. Hundreds of tiny SMD components soldered in late evenings, all of them coming together, putting them inside one box to have an engine control unit, having it work using entirely student build technology, outperforming technology that we spent 20,000+ euro on. That was a pure moment of satisfaction, unrivaled by anything that has happened since.
Okay. And are there any redundancies built into the electronics to prevent failures?
So with the way that we've built the electronic system, we have a lot of redundant boards and such. We have safety measures on all of the different PCBs. We've got resettable fuses, for example. We've got diodes to prevent back EMF induction whenever we activate a valve. We've got multiple different channels for activating the recovery system. We've got redundancy wherever it matters. And we also have telemetry to transmit our onboard data down to our control point. But on every single PCB in the rocket, which I think is about 12, we have an SD card for logging the data locally. So if the rocket crashes and we don't get good telemetry, we can go dig it up and find the individual data itself.
To still know what happened, what went wrong, or what do you get out of that information?
So the data that you have on the rocket is very useful for forensics because we're a student team, we're here to learn, And if the rocket doesn't go perfectly, and if something goes wrong, we still want to be able to know where we went wrong so we can improve and build from that. It's very important to have forensic data available to us. This is known. It's in the avionics field. There are black boxes on every single plane flying around the world. So you want to make sure that if you do things well, you know how you managed it. That's documentation. And if things go poorly, you want to know what happened and how do you prevent it next time. And we want to make sure that our next rocket succeeds as well.
Okay. Then I only have one more question for you. Are you planning to stay in there, or what are your plans for the future?
Yes, I am planning on staying in there. I've just done a board year, and now going forward, I am the new team manager for the flagship following Stratos 5. So I'll be leading the project Helix, which aims to be a much more simple rocket, which goes to a much higher altitude with a much less complex system.
And how high is Helix going to go?
Well, we're currently aiming to go to 120 kilometers, but that depends on a number of factors and how it all comes together. As with any project, you don't know how it'll turn out until you actually create it.
Well, yes, yes.
Yeah.
Okay. Well, thank you for your time, and well, good luck with Helix. And
Thank you, thank you.
hi, how are you?
I'm fine.
Could you introduce yourself a little bit?
I'm Anvita Gagil, in the third year of Aerospace Engineering Bachelor, and I was in the Electronics and Control sub-team for Stratos for the last year or so.
Right. And what did you do in the electronics department?
So I was focusing on the power management system, and in that I mainly worked on three things. So firstly, I was in charge of making the power budget, because we need to figure out how much power to make to get requirements for the power management system, the batteries, things like that. So I was basically just going up to the other sub-teams, like asking recovery how much their pyros draw, how much power they draw, how long will they be on for. Same for propulsion, what kind of valves they use, how many valves they use, when will they be on for, how long will they be on, things like that. And then I made a huge spreadsheet basically that showed what is the peak power draw, so how many batteries need to be in series, and what is the battery life that they need to have, so how many watt hours basically. That was the first thing. Secondly, I needed to implement some circuit that regulates the voltage to 24 volts, because the batteries and also the power supply on the ground can have some variable voltage depending on how charged the batteries are. So there's a voltage regulation circuit that makes sure it's 24 volts so that it is safer for the components downstream. And the third thing that I had to do was the switching between umbilical on the ground and batteries on board. So that's basically where, when the rocket is on the launch pad, it's unclear how long it will stay on the launch pad in EuRoC. It could be up to 6 hours even, depending on how the launch windows work. So instead of having batteries on board that can power the rocket for so long, because it's going to have some power for valves, for sensors that measure things, all of that, then instead of having this power capability on board, there's a ground power supply, and this connects to the rocket using a wire called the umbilical. And how it works is that when the rocket launches, it basically pulls on the wire, and the connector is built in such a way that it just pulls it off. So for that, it can create some power spikes when the connector is pulled off, because it is suddenly pulled off. So it goes from the one power source to the batteries. And that switching has to be smooth without disrupting the supply of power, because that can mess with the valves and cause some oxygen leaking and things like that. And you do not want oxygen leaking at the minute when the engine is igniting, right? So there was some circuit, there were some MOSFETs that make sure that this transition goes safely. And in the end, we also implemented a microcontroller that can talk to the ground station, so that us in the command post can directly switch it before the umbilical is already pulled.
Okay, and of course you did a lot. What was like the biggest challenge for you this year?
I think the biggest challenge was mainly that, like, when I joined the team, I didn't know anything about how to make PCBs. And it was like, in 1 year, you need to have made your own PCB. So it was like quite a steep learning curve where you learn a lot of things quickly. And it was really great because everyone in Stratos Electronics helped me a lot. And all of the people, they showed me how to use Altium for making a PCB, how to choose components, how to read data sheets, and other things about impedances, resistances, things like that.
Okay, that's nice. And what was for you then the most exciting moment during this year?
I think the most exciting moment would probably be when the PCB was actually ready for manufacturing, and I saw it like when the rocket was manufactured. It was there, real life, in the rocket, on the stand, and that was, I think, the coolest moment, because it's like one whole year of work has now come together in a real thing that will really launch.
And you can physically see.
Yes.
Yeah.
Because until then it was just on the computer with the designing on Altium. So.
And then I have just one more question for you. Are you planning to stay in there? And if so, what are you going to do?
Yes, I'm definitely planning to stay in there for the last year of my bachelor's. And now that there is Stratos is going to launch, then I'm not going to have more for Stratos. So I'm joining other teams in there. So one I've joined is Haystack, where we are building a rocket that will launch at the end of this year. And I'm working on the, it's a 2-stage rocket. We're trying to beat the speed record at ASCA. So I'm working on the stage separation mechanism and also on installing cameras for it. And the other thing is that I'm working for turbo machinery. So for that one, I'm working on the battery system. So also what I did in Stratos, I'm continuing.
Sounds like a lot to do, a lot of challenges to overcome again.
Yes, it will be fun.
I wish you a lot of luck and fun.
Yes, thank you. Thank you.
All right. So, well, those were some interviews. We did see that the EuRoC livestream has a launch imminent. I'm not sure exactly which team it is, but
It seems that we are going to get a little bit of appetizer before our launch by seeing a different team. So we are going to cut to the EuRoC live stream where we might get to see a rocket launch live.
T-minus 40. T-minus 30. Arming. T-minus 20. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. Lift off. Trajectory good. 5,000 meter. 6,000. 7,000. 8,000 meter. Air brakes deployed. 9,000.
all right. Well, that was a very cool launch. We're still not sure which team it was.
They are clapping because they are very
yeah.
happy. They are now
Well, they're doing another replay.
watching to the
Drone
sky.
deployed.
And they are cheering.
Do you have anything to add to this?
Descending at 30
It
meter
was
per
a
second.
great launch.
Wow, looks fantastic.
Let's hope ours does something similar.
9,000 meters.
They are
descending
very
Yes,
at
that is
40
the
meters
hope.
per
because they
second.
reached their goal.
Right.
They are celebrating, they are
Um,
smiling. This
There
is
was
a
a
very
question when
exciting
the
moment
launch window is
for them
opening.
because
We
they reached their
expect
goal. It was a
around
lot
4
of
to
work, a lot of
6
work days, a
to
lot
have
of
our
sleepless
launch
nights,
window for the
days,
people that are
months,
really waiting
and
for this.
years of work.
That's 4 to
And
6
they did
Amsterdam
it.
time, which is 3 to 5 Portugal time. So where the rocket is launching in EuRoC.
We are at 7,500 meters.
In the
The drone
meantime,
is yellow. Looking for yellow drone
we can go
shoots,
and watch
the
some
main is
old hot
orange
fire
and
videos from
purple.
our engine. So, yeah.
Seven, 6, 5, 4, 3, 2, 1.
All right, so I think the rocket was spotted, the one that just
1,000
launched
meter.
prior.
And we are getting news that it is just now coming down after reaching apogee. So after having seen some electronics interviews and some
600
cool
meters.
engine tests of various levels of success, we are gonna go back to the EuRoC live stream so we can see what's going on with the rocket.
Beautiful.
They just saw the parachutes and they are very happy. They reached their goal. We see a lot of smiles. They are so happy. It's so great to see
For
here the
information, the rocket
excitement
is now
and the
at
happiness.
1.7 kilometer, 1.7 downrange.
What a great launch. Amazing.
Main deployed on the nose cone. Nose cone touchdown. Descending at 5 meters per second. Touchdown.
And
Beautiful,
we have
soft
touchdown.
descent
Amazing.
and landing.
They are-
Amazing flight.
they are
Thank you,
very,
Team
very
Artists.
happy. So, Team Linder, you did it.
Yeah, it worked very well. We're all very happy that it worked so fine. Yeah,
You had a great launch, a great touchdown.
Everything is planned. So from the moment we launched on, it was, I think, exactly as planned.
Did you had any problems this morning? It was everything okay? Yeah?
Yes, this morning was a little bit chaotic and some people did not sleep the whole night, but we made it.
Amazing. What are you feeling now?
Well, I'm relieved from some pressure and very happy that this project is on its peak now.
You reached the 9K, right?
When I heard that correctly on the radio, it was 9K and a few meters above, so very close.
And what is your team feeling and thinking? I saw a lot of smiles, a lot of cheering. They are they are celebrating.
Yeah, they're celebrating, and they're totally right celebrating now. They deserve it. They did a great job. Just a few minutes before launch, we had to bring the whole team back to the launch rail and rotate the whole rocket, including the launch rail. This was only possible because 20 people were running down, lifting together and rotating that heavy thing. And I'm very impressed and very proud on that team.
And do you believe you can?
So we just watched that beautiful landing of our fellow team at EuRoC live with you guys. And so we would like to tell you a little bit about what exactly we saw, because our parachute system is quite similar. Our recovery system is very similar to the one we have just seen. So you saw on that one, there was a little parachute that came up before the big one. That is called the drogue. And it is used so that the big parachute doesn't induce a sudden jolt that causes the rocket to experience loads that it was not designed for. And to hear more about this system, we are going to cut to our recovery guy, Dan. And so now you get to see his interview. So let's cut to that.
Hi, could you introduce yourself?
Of course. I am Dan. I am part of recovery, so I work mostly on getting the rocket back to Earth. I am a third year aerospace student at the Faculty of Aerospace at TU Delft. And
What did you work on this year for Stratos?
so, as a part of recovery, we had to split up the tasks, of course. So I didn't actually work on any of the parachutes. I worked on getting the parachutes in the air. So that means that I made sure the nose cone deploys at apogee, and it deploys without destroying anything. So what we did is we looked at the design decisions that previous years made and assessed that because of the change of requirements around the summer of this year, that we needed to adapt our system. So we changed from a system called a clamp band into a system called a slip fit, which I designed and produced together with a teammate Anita. Besides that, we also made sure that the nose cone actually comes off. So the slip fit is just to ensure the nose cone stays on during flight. Then the system, which we called cold gas deployment devices, that is the system that made sure the nose cone actually comes off after flight. Well, after the rocket reaches its highest point and needs to come down again.
How does the nose cone deploy?
So how it works is that we have a couple of CO2 canisters, which are easily sourced, which is a reason why we chose this. They get punctured by a certain system that we made, we partially designed, but mostly took it from experienced people and adapted it a bit to our requirements. So that punctures the CO2 canisters, making the gas inside expand to a large volume, which will exert a pressure, which will exert force on the nose cone, pushing it out, which will then pull out the parachutes.
Right. And what was the biggest challenge for you this year?
So a large challenge for us was just getting everything on paper correctly and getting a good overview, because this is such a large project with so many people that it can be quite hard to, see the forest through the trees. So that was definitely a big challenge. Besides that, it's just designing something for a rocket so large, it can be quite different than what we're used to for smaller rockets. So it was really kind of a different kind of scope of what we're used to. So that's how we kind of figured out like what we needed to do and what we not needed to do. That's, you know, we made mistakes and then you adapt to that and you find something that does work in the end.
Okay. And of course, you're part of recovery, so recovery made a parachute. Could you tell a bit more about how our recovery system and parachute works?
So, a parachute, you mean how a parachute works?
Well, how our parachute works, because I heard it's a multiple stage parachute.
Yes.
Could you give us a bit of rundown of that?
So after the nose cone deploys, we first inflate a drogue chute, which is like a smaller chute meant to kind of control our terminal velocity of a rocket before our actual parachute deploys. This drogue parachute also pulls out our main parachute after we've descended a while. Another reason that we needed the parachute, the drogue parachute, was because there's quite strict requirements on how far the rocket can stray after apogee. So that's another reason. Then after the drogue deploys and it descends to about 700 meters, we deploy our main parachute using a 3-ring system, which transfers tension from a line connected to the rocket to a line connected to a parachute bag, which holds our main. Now, because the tension is transferred, this pulls out the main out of the bag, which deploys the main parachute. At this point, the main parachute is still reefed, which means that we've decreased its maximum diameter by tying a line around it so that it's not too large and we don't stray too far from our descent area that we're allowed to land in. Then after another couple hundred meters, so around 400 meters, we unreef, which means we cut the line, we fully deploy our main, and that way we reach our descent velocity that we are required to.
Right. And then, what was for you the most exciting moment for you this year?
So, the most exciting moment for me personally was seeing our system come together with a test we did not too long ago, where we got all the work we did. We assembled it together and we did a test on it. So we assembled all our cold gas deployment devices. We put them in a recovery bay. We put all the parachutes in. We put the nose cone in. We attached shear bolts, and we actually put it in the wind tunnel and tried to deploy the nose cone and go through the entire recovery sequence, kind of simulated. Seeing it all come together, it was really nice. You know, you've been working a year on this, and if this fails, you're really, really in a terrible state. So it was quite a nice moment to see that we are not completely dead, and we can actually launch, and our system works. So that was great.
Sounds like a very tense situation, and then it succeeds. It's nice.
Yes, exactly.
Just one more question for you. Are you planning to stay in there, or what are your plans for the next year?
So, my plans for this year are, of course, to stay in there. Me and some friends actually started our own team. We're launching a tiny small rocket with some very big goals. We're developing air brakes as a team, so that's never really been done successfully in there. So that's a nice challenge.
What's the name of the team?
It's Quetzalcoatl. It's the Aztec god of flight. Then besides that, I'm working on a team that actually got expelled from Stratos, which is turbo machinery, which we are planning to take the engine from Stratos that we are flying on and put a turbo pump in it to increase the pressures we could run at, and to also decrease the mass that the entire system is by not needing a pressure vessel like helium to pressurize the system. So we're testing that sometime this year. Then besides that, I'm also focusing a lot on safety within there. So just making stuff run safely. We handle explosives, so that's really, it's an important task and a very interesting one as well.
Okay. Well, nice, and I want to wish you much luck for your next years within that. And thank you for this interview.
Thank you very much.
Well, so that was very interesting, and thank you for Dan for also helping us right now with our setup. Yeah, so right now we also have some videos for the parachute that we're using.
So that you can get more information about the drogue that you just saw and you heard about.
Yeah. So we have an old rogue, which we can show some footage of. Also, these all were tested at the OpenJet facility at the TU Delft wind tunnels. Yeah, so let's show the drogue footage.
Hi, could you introduce yourself?
Of course. I am Dan. I am part of recovery, so I work mostly.
Looks good to me. Yeah, I'm seeing that as well. Any concerns from your side on that?
Nothing we can do about that, so go ahead and go to 15 and we'll go for 10.
Copy that, ramping up to 15 meters per second.
Is it so turbulent because
It's too big for the chute. It's too big for the wind tunnel. That's why it's so turbulent. Also, it seems like your line that's going to your bag is like wound around the chute.
Ribbons. Copy that, I'm good to go to 20.
It's a design choice.
Yeah. Copy that, going to 20 starting now.
Actually, let's add drive.
How big is that?
Can it be quiet again in the room, please? Because we're gonna go to 20, which might.
Okay.
So you just saw the two drogues that we had launched, that we had tested in the wind tunnel, at the TU Delft. So the orange one was the older drogue, and the pink one is the newer one. And these both were tested in May at the wind tunnel. And you might be asking, why exactly is there a hole at the top of them? Normally, a parachute should not be letting air through, right? Well, the thing is that there is a hole in them to allow the air to flow instead of going around the parachute to go through it so that it doesn't block the airflow and cause turbulence. And it was designed using various parameters. What? Okay. The first video shows the pull-out test of pulling out the main during flight, but you will notice that there is not actually a main parachute over there. That's because the main parachute is so big, it doesn't actually fit in the wind tunnel. It's 5 meters in diameter, and that's bigger than the wind tunnel itself. And in fact, if we were able to test it, if we had actually put it in that wind tunnel, it would have had enough force to rip out the test bench from the wind tunnel itself. So it's a very big thing. You saw that the drogue itself was like quite big. There were people behind in the background for scale, and in total, it's going to be a lot of forces that the parachutes are going to have to carry. We also have videos of the main parachute that will come later. But first, do you want to add anything?
I think you did it perfectly. So yeah, good job.
All right, then we will show you some videos of the main parachute.
Up to 15 meters per second.
That's fine.
Can we go higher? They're not there anymore?
Oh shit.
Yeah. Okay. Okay.
Looks pretty good. Yeah, I think it's already touching.
It's very stable as well.
That's not the problem.
Oh yeah, but the load that it's pulling. Yeah. It's kind of small. Like the between the reefing.
Well, so you can see the videos where they had to hold up the parachute. Very interesting way of testing, of course.
And we saw the question in the live chat that if we could not fit the parachute in the wind tunnel, how were we able to test it to confirm that it would actually work? Well, as you can see, we did manage to test it by reefing it. Reefing is where we tie some strings to the parachute in such a way that we can test it, but not fully open. So you can see in the video as well that there's a flapping rectangle things. It's basically because it has been tied up in such a way that we can still do the test in our wind tunnel, but not completely open the parachute so that we don't have the test bench experience too many forces and we don't take up too much area of the wind tunnel. So we still managed to test the parachute, so we know that it will work, but we have not tested it fully open because that could be unsafe for bench, for wind tunnel, for the people in the wind tunnel. Would you like to tell them about the people holding it?
I'm actually not sure who is holding it right now, but yeah, they had to they had to hold the parachute because otherwise it would just fall to the ground due to the weight.
It's such a big parachute that in small winds, like up to 15 meters per second, it would be too heavy to hold itself up in the air. So to get it started, because of course the wind tunnel starts not at directly 60 meters per second, it slowly ramps up. We had two people holding the parachute so that it would be able to stabilize itself when the strong winds were produced by the wind tunnel. So that's why we had two people holding it. I think you can see one of them in the video. They are our amazing recovery people who are part of the test.
Yeah. I think for now, I'm not sure what the current update is for the EuRoC live stream.
But we are getting the info on it from our behind the cameras technician guy.
So there was another question about our current altitude goals, and we will be trying to reach 3 kilometers, which is according to our current simulations. Yeah, updates we just got in. But yeah, that doesn't sound very high, but due to EuRoC and other conditions, we will have a lower altitude for 3 kilometers. But yes, it is what it is.
The point of keeping the altitude low is that we don't want to be overambitious with testing our liquid engine with LOX and ethanol engine, along with a high altitude would be many things to try and optimize for. So we've picked that we want to demonstrate our Sparrow engine and focus on that rather than high altitudes like Helix, for example.
And it should also be noted that right now this is the most powerful student produced rocket in the world. Liquid rocket, sorry. Should be saying that as well. Yeah, I think some interesting facts about the rocket is, of course, we are using LOX and ethanol, so two liquids. LOX being liquid oxygen, and ethanol is maybe what some of you might be drinking now and then. But yeah, how it basically works is we have a LOX tank, we have an ethanol tank, and a pressure tank. In our case, we use helium. Um, the helium pressurizes both tanks, which then are fed into the engine, which at the engine will combust after ignition. We've seen some videos before as well. I think it might be nice to pull up some more videos. Um, these are all from the days of Sparrow. So Sparrow first was a team that just made the engine, the DLX 150, made the A, B, and C versions, which, yeah, they just wanted to build the engine, and later Stratos 5 became the idea to put the engine in a rocket, which is what we're attempting to launch today. Yeah, so here are some of the hot fire videos.
That's fine.
Can we go higher? They're not there anymore?
Oh shit.
Yeah. Okay.
Seven, 6, 5, 4, 3, 2, 1.
All right. Well, those were some beautiful videos.
And we will tell you more about the facility where they were tested in a bit. But first, we are going to hear about some facts about these tests.
Yeah, so how the system is ignited is pretty interesting because it's a very old system. We literally have just a stick going into the engine with some steel wool, which we ignite, and then the moment the liquid oxygen and the ethanol mix with the sparks from the steel wool, it'll ignite. Yeah, these ignitions are sometimes can go wrong at times. We've had times where the plug is pushed out, but most of the times these have worked, as you can be seen with the videos we've looked at. One of the ways how we do our ignition is by having a oxygen-rich environment. So we restrict the fuel the fuel flow, the ethanol flow, with a restrictor valve. The LOX valve, the main valve or the LOX, will just be doing its constant pressure. Afterwards, after it has ignited, the main valve for the restrictor valve will completely open for the ethanol flow, having your full combustion. As you can also see, there are mock diamonds, which is the beautiful patterns you can see. They look really nice, but it is technically a property of inefficiency. The rocket was designed to go to about 50 kilometers, so the higher the altitude, the more efficient it would have become.
The way that the Mach diamonds work is that because the nozzle is shaped as a convergent divergence nozzle, that means that it converges to a very narrow point and then expands to a very wide exit. Because of this, the gas also expands, and it should expand to around the same pressure as the ambient. If it expands less, it goes out and then bounces in because it is overexpanded, the pressure is low, higher pressure outside, it gets pushed in, bounces, Mach diamonds, and then expands again. So that's why you get the diamond shape. And this means that the flow is slightly lower pressured at the exit than it should be compared to the pressure around it. But this is because there's lower pressure at higher altitudes. So then when we were testing at sea level, or even lower than sea level because this is the Netherlands, then you get those Mach diamonds because it is lower pressure, it is higher pressure outside, and the flow is designed for higher altitudes, lower pressure, so it is overexpanded, causing the Mach diamonds. So the theory is that you will not get these Mach diamonds when the rocket is actually flying, but
Yeah.
the rocket was supposed to go for up to 50 kilometers, and now it is going for only 3, so we'll probably still see them the whole way.
At least they're very beautiful. So
they are very nice. They look very nice.
We will go back to an interview, mine interview actually, which I'll also talk a bit more about my part in Stratos. So
let's cut to that.
Let's cut to that.
Hi, could you introduce yourself and what you did in Stratos?
I'm Nathan, and I've mostly worked as a part-timer for Propulsion, and yeah, that was the department I was working in.
Okay, and what inside the department did you work on?
I mostly helped with testing, a little bit of manufacturing, but that was only a couple of times. So I think driving to the military base and stuff, and setting up stuff, and also actual testing, of course.
Okay, and during those tests, what was your role?
I've been mostly support, but I've also been TO.
Okay.
Which meant that I had to look for leaks and make sure that the system is operating correctly. Mostly means you're in the most dangerous position because if anything goes wrong, you're the one to first notice it.
Okay.
But that's
you're getting the blast of the explosion.
Yeah, exactly.
Yeah. Okay, and then what was your biggest challenge during the campaign?
I think one of the hot fire campaigns we were trying to we were trying to look for leaks, of course, and we just kept on finding leaks, and we noticed some other problems with the system. And I think in the end we didn't even do the hot fire, so that was kind of sad.
That's just for people that are not really technical. Leaks are a bad thing, right?
Yes.
Why?
Well, one way to talk about propulsion is we call it plumbing, and just like with a bathroom, yeah, you don't want leaks, because especially the fact is that we are using like ethanol or LOX, which is even more dangerous. You don't want to be spewing out everywhere while you're working on the system.
Yeah. Why is liquid oxygen or LOX so dangerous?
Well, one of the things is very cold, so yeah, you don't want to touch any of the parts that's already been touched by LOX. But I think the most dangerous thing is that it's liquid oxygen, so it will burn anything that's combustible, basically. Clothes, hair, yeah, you don't want that stuff on you.
Fair. And what was for you the most exciting part of being part of Stratos? Or is there any particular moment that you can pin out?
I think for me, it was the first time I was with one of the hot fires last year. That was honestly really amazing, just to be there and to see the engine actually go off. And, yeah, and hearing the rumble in the background. Of course, you were in a safe location, so. But no, that was definitely one of the coolest things I've seen.
And are there any? You will be in the live stream, right?
Yes.
Hopefully. What are your goals during the live stream? Do you want to entertain people, or what do you want to do during the live stream?
I think, of course, keep people entertained, because it might take a while. But yeah, I think I'll just mostly talk about the rocket, the project. Try to have some interviews go by from other people, other departments. Yeah, and of course, hopefully show the launch when it happens, if it happens.
Okay, and then I have one more question for you. Are you planning on continuing it within there, or later on in the rocketry sector in the industry?
Yeah, so right now I'm in my bachelor, so I'm definitely planning on doing a master's here and also keeping or staying within there, so to speak. I'm also part of Chimera, which is kind of continuing the liquid oxygen program, so to speak. So I'll definitely have a couple more years working.
What kind of project is Chimera?
So they work on a hybrid engine, so it's a bit different than what we're using right now with Stratos. But it's very simple. You have a solid fuel, and you have a liquid oxidizer, so LOX in this case, of course. And that's the difference with normal liquid biopropellants, where ethanol, of course, is a liquid.
Well, then I wish you a lot of luck with Chimera, and people will see you during the live stream. Hopefully. Thank you.
All right, thank you, Nathan, for that wonderful interview.
Yes.
Now, before we continue with the interviews, I've just seen the question about the parachute test. So the question is that if we tested the parachute horizontally in the wind tunnel, how can we be sure that this translates to an actual flight and the kind of forces that we will experience during flight? We have done some modeling for these things on a computer, so we know that it will translate properly. And we have used the wind tunnel as well to model the kind of forces that we will experience during flight. But yes, you are right that all of the forces are not equally translated. And one solution for this is to literally just take the parachute up in a plane, a helicopter, something like that, and just throw it and see what it does. We actually were going to do this. We had a helicopter that we were going to take the parachute up in and actually just throw it out of the helicopter to see what it does. But unfortunately, the helicopter company had something else that they needed to do with the helicopter. Is also skydivers. You just basically use the parachute for skydiving. But we didn't get any volunteer skydivers because student built parachute. So yeah, we did not test it like that because that might be unsafe considering that it's a test parachute. We don't want to attach a person to it because that may end badly. So we have done a much safer wind tunnel test because up there we value safety more than anything else. So no matter how much we trust the parachute, we are not going to put a person on it. So yeah, we are going to test it. We have tested it in the wind tunnel, and we think that this isn't. We are confident enough with these tests that it will work also with the rocket. And now we can segue to the next interview, that is from structures. Oh, but before that, we are getting important news. Do you want to say it?
Yeah, sure. So there's going to be a new launch window at 2. This is not for Stratos. Skyward, EPFL, War, Trust, and Ares will be launching after so still 4 o'clock our time, Amsterdam time, we will have our launch window. But now, I'll repeat myself, Skyward, EPFL, War, Trust, and Iris are launching at 2 o'clock, so in a couple minutes.
So not Stratos, which means that right now the pad is inaccessible to Stratos because the other teams are launching.
And yes, so here are some structured interviews.
Yep.
Hi, could
Hi.
you introduce yourself?
Yes, I'm Matisse, and I was the chief engineer for Stratos 5 Year 2.
What were your tasks during the year 2 of Stratos 5?
My tasks were mainly related to just keeping the team informed about each other, so facilitating communication, but also having an overview of all the technical matters in the project. So that's organizing periodic meetings to discuss any technical issues that might have come up. But also I would sometimes help out within departments or machine stuff.
Okay, and well, you were the guy between the departments. How did you make sure that the departments were actually working together and not were becoming islands?
Yeah, it's not an easy task, but yeah, like I mentioned, one part of it is having meetings once in a while, but also providing tools for people, or also maintaining those tools to have sort of a single source of truth. So, for instance, we used a website for that, software, where we have all the the numbers that are related to our rockets, and then if anything changes, other things change as well, and also tools for having our documentation in order. Those are kind of things that you can do to keep the team communicating and on the same page.
And what if, for example, someone didn't update the numbers into the system? How would you tackle that? How did you tackle that?
Yeah, well, that would happen quite often actually, but yeah, then you just have to individually go after them and ask them to update those things, because yeah, we did see sometimes, and if it didn't happen, then suddenly you're dealing with inconsistencies, and then yeah, you start getting into what sometimes called integration hell or systems engineering hell, where nothing works together anymore.
And then it became islands, but
exactly.
And well, of course, you guys did a campaign during your year.
Mm-hmm.
What was it like, and was your task during that campaign?
Yeah, so we had one hot fire campaign. It was really far at the end. It was in April/May. This was related because the test cell was just not available earlier in the year. So we were not successful in firing the engine that time because we were having a lot of setbacks. Some of them also related to a new part of the system that we were testing that wasn't tested before, like the ECU and the dome-loaded regulators. I was most days I was test leader, so it was just a lot of it was also focusing on logistics, so getting the cars for people to go and just keeping an overview of everything.
And also some non-logistical stuff, so more technical, or
it was less technical. I was mainly like the technical stuff was mainly done by the test. What's the name?
TC.
Yeah, TC. And
test
also
conductor, I think.
Yeah, could be. Test conductor, I think. But it was mainly them. Also, like I was less. There were some more experienced people with like the hot fire setup there, with which I was less involved. I was more involved with just the rocket itself and the design process of that. So in that sense, the hot fire setup is a bit different. Of course, if you had more hot fires, I would have also loved to be more technically involved, also with the hot fire setup. But
well, maybe in the future. Well, of course, you are in year 2 in a 3-year project. How was it to be like the middle year?
Yeah, it was an interesting position to be in because, of course, we inherit this design or this preliminary design already from the previous year, which was actually, they had a lot of good progress, a lot of design tools already set up as well. And then but we're also not really in that we're not going to be in that final stretch ourselves. So for instance, we were very we wouldn't pay or we wouldn't spend a lot of money because a lot of it we were like we need to save up for the launch campaign and such. But yeah, a big part of it is getting that design and then continuing on that, and part of it we also figured out some things that maybe could have been better. So that's kind of the position that you're in.
Okay. And what was the most exciting moment for you that year? Or Stratos in general?
So for me that year, it's somewhere at the start of the year we figured out that because at the start in year one the goal was really to go high with the rocket, and we figured out at the start of the year that we weren't probably gonna go very high, so we decided to more pivot towards trying to really just launch as simple as possible. So not aim for high altitude, but just aim for that we can launch reliably. And this pivot period, where we would pivot to this new scope, took more than a month. Of course, we did trade-offs. We did a lot of sessions with feedback. We talked to industry. We talked to former DARE members, and then you have to report everything and ask people what they thought. And eventually, we decided to pivot to this smaller version of the rocket that would be more easily machinable by us, or would be less reliant on other things. So it was quite exciting once we got that done and that we could actually start designing again. So yeah, that was quite exciting for me.
Okay. And then I have one more last question for you. What will you do after? You finished Stratos. What did you go and do after Stratos?
Yeah, I joined another liquid biprop team in there. I joined Axolotl, which is just a small-scale liquid biprop engine. I also joined PIP, which is the Parachute Investigation Project. There I mainly did machining and just, to use the Dutch word, burning, which is just
getting stuff done.
Getting stuff done, exactly. And I also I joined the activities committee where I was the chair of for a year. So yeah, I'm in those things. I'm still active as well.
So many projects.
Yeah. There's that's the fun thing. You can, once you're done with one project, you can just join another project, and that's the great thing in there. There's a lot of projects that you can join.
Well, then I want to thank you for your time and wish you luck with Axolotl and all the other teams you are doing.
Thank you.
Well, that was a very interesting interview.
With a nice cameo from Florian in the background.
Yes, as you've seen before. So we would like to talk about electronics, which is a very important part and subsystem of any rocket, because without it you can't really go anywhere. So Anvita will now tell more about it.
Well, we've already seen 2 videos about electronics, including mine, but now we will see some more about them. But before that, I'll tell you a little bit about the telemetry happening on the rocket. So one of the boards that on the rocket is for apogee detection, for launch detection, things like that. It has basically an accelerometer that measures how much the rocket is accelerating. So when it's on the launch tower, it is stationary, so acceleration is 0. Then it accelerates, so launches. That's when you know that the launch has happened. And then apogee, it slows down until it stops, then it starts coming down. So acceleration 0 again. That's how you know you've reached apogee. So there is a telemetry board that monitors this. So we know that we've reached apogee so that we are able to deploy the parachute at the correct time. Because of course, if you deploy the parachute before apogee, it is upside down, which, is not great because you will not reach apogee then. That board allows us to find when we have reached apogee, and then when a few seconds after that, it deploys the parachute. Another thing it can do is altitude detection, which is also important because we need to make sure not to undershoot, overshoot, things like that. Or if we do, we want this data for future missions and further developing our systems. We also had a flight computer that we had tested on a different rocket called. But the thing with that test is that the rocket went ballistic because of some problem with the recovery system. And because of that, the SD card data was not recoverable because the flight computer is in the nose cone, and the rocket, by going ballistic, had landed nose cone first. So that data was destroyed. But that's fine because we have still done tests by just not inside a rocket, but otherwise just moving it around to see that it makes sure that it can detect acceleration, detect altitude, things like that. So we are still fairly sure that it will work. And now we can go with the interviews of the different electronics people.
Could you introduce yourself?
Hi, my name is Jan. I have worked on the electronics for Stratos 5 for the past 1.5 years. So
quite some Stratos experience. And what kind of electronics did you work on?
I mostly worked on the ECU, the software side, and also the power board, the software side. So I didn't really do any of the hardware designing, but I did write a lot of the code for it. And then I worked on the thermocouple board as well with a few other people.
Okay. And what was the biggest challenge for you during Stratos?
The biggest challenge? It's you need to learn a lot of new things, technologies, and you're basically like it's your own responsibility to learn those things. Like you work with embedded systems, which are quite a bit different from programming regular computer programs, and you need to read through tens of thousands of pages of documentation to figure out a specific thing about some communication protocol. So it's a lot of reading documentation and then figuring out how it works by just testing and messing around with it. So it's a lot of figuring out stuff you have never done before.
Okay. And is there any particular problem that you encountered that you really stuck by you, that you learned from it?
Well, a lot of small communication problems, which I had to work with a logic analyzer and debug the actual communication stuff, and then figure out that it was addressing the wrong pin, and then all of a sudden it worked, and then another time the communication, it was a single bit was not set correctly, which meant the entire communications were just broken. Which it took me 2 days, 3 days to figure it out, and then at some point I just saw one single bit, and it worked.
That's software for you, coding, right?
Yeah, that's software.
Yeah. And what was the most exciting or rewarding moment for you during this year?
It's definitely the hot fires in general, the campaigns. It's so much fun just being there, but then actually sitting there and doing the filling, doing the pre-chilling, and you get closer and closer to the actual moment of hot fire, especially the last hot fire before EuRoC, the verification hot fire. It was 3 days of the busiest days. I had to be there, and we were all on the edge of is it gonna work, is it not gonna work, and then we actually saw it fire, and just the adrenaline rush of seeing it fire, and after 3 days of fixing stuff and then breaking again and then fixing more stuff.
Okay, and what did you typically do during such a hot fire camp?
I mostly was in part of the command post. So as electronics, you of course connect all the cables, connect all the systems, and then of course you're gonna find problems. And then it's your role to figure it out, test stuff, and it's a lot of communicating with portos to people who are either standing by the thing and to see if it actually clicks when you could press the button in the other room, and then it's a lot of that. And then on the other side, it's during the actual procedures, you power the valves to do the filling, and you actually go through the procedures, you communicate a lot with the people by the system.
Because the command post, just to clarify, is in a different area than where the test is being done.
Yeah, of course. You need to sit in a safe place, so it's separated by 2 very thick walls. But you communicate with the people who are actually there, who are working with the system. you call out pressures, you like open valves when they ask for it, and then like when actually you start hot firing, you actually like you basically press the button. You don't press the button, but another person presses the button, and you like keep an eye on the system, pressures, whatever. If anything weird happens, you call it out. So it's like a lot of communicating.
And how will that, because you're going to the launch campaign, how will that be during the launch campaign? What will be your role?
I am the observer of CP, so my task is mostly like to take notes, to like observe the system, like read out pressures, read out data, and like by doing that, you keep the other people of CP. So they can still do the work. They don't have to monitor the system the entire time. Like you take a bit of the responsibility of actually looking at keeping an eye on the pressures when people are close to the system, because you don't want anything dangerous. That's very important.
Yeah. And then I have one more question for you, one last one. Will you stay in there, and what will you do in the future? Do you have
I will
any
definitely
idea?
stay in there. It's a very fun experience, and I don't want to miss out on anything. I'm gonna personally join Turbo Machinery, which is basically kind of the continuation of the development of the engine Stratos is using, since it was originally designed for a turbo pump, but because of design issues, like turbo pumps are very hard to design and manufacture and test. We have chosen to not use it for this rocket, but the end, like the pump is still in development, and we hope to in the future be able to hot fire the engine with a pump as it was originally designed. So that's what we're gonna continue working on. So I hope to see that happen. And besides that, in general, like I hope to stay within the association, maybe within other teams.
Sounds like great fun. Well, good luck with that, and good luck at the launch pad.
Yeah.
Then,
hi.
Could you introduce yourself?
Hi, I'm Federico. I'm part of the Stratos 5 team in the electronics team specifically.
Great. And what did you do this year for electronics?
This year with the electronics team, I worked on the reefing boxes and the reefing boards. These boards are very tiny boards, about 4 to 3 centimeters, which have the objective to unreef the main parachute. As we'll see, the main parachute is quite big, and it has been reefed for the recovery reasons. So my precise job was to design this board which could detect the pressure and so the altitude and count a timer to unreef the main parachute. This board uses a pyro, a small detonating device that cuts the main line around the main parachute and opens it up. So this creates more drag, and of course the rocket will slow down even more. How does this mechanism work? This mechanism is basically activated the moment the main parachute is actually pulled out of its bag. So when the rocket is already descending. This is activated through a mini audio jack like the ones we have in our phones, and it's just pulled by the main parachute when it comes out of its own bag. And a timer starts together with an altitude detector, which decides whether the timer will prevail or the altitude difference will prevail on unreef the main parachute. This board was designed through different softwares, coded all by myself, and it was tested also both with the pressure sensor, so with a little vacuum chamber to actually detect the board would ignite the pyro, but also just counting the timers with the seconds with a timer. And yeah, and then I 3D printed the boxes that could actually be inside the main board, the reefing board, and attached those to the main parachute.
And then I have a question, why did you choose for a timer and the altitude detection? Why the two separate?
So after a discussion with the recovery team, we decided that a redundant system would be better, as we always have in aerospace, for example in aircraft, even in rockets, and in all the aerospace equipment. So we decided to have both a pressure sensor and a timer, just for redundancy.
Okay, just if one fails, the other
Exactly,
one.
yeah.
Okay. Yes. And then what was for you the biggest challenge this year?
The biggest challenge for me was learn all this stuff about electronics. So I was completely new to this world, as I'm an aerospace engineer, and we don't do much electronics or any basically physics, as which resistors, capacitors. So it was a whole new different world I had to learn through YouTube videos, mini courses, everything basically free, available online. And it was really exciting for me to learn this way and to actually project something, design something myself, and I will actually see work in the actual Stratos 5 rocket.
Okay. And what was then for you this year the most exciting moment?
The most exciting moment was actually having the drogue rift parachute in the wind tunnel and actually see my reefing box actually unreef the drogue parachute. This was just a testing. In fact, the reefing will actually be on the main parachute, but it couldn't fit in the wind tunnel, so we decided to put it on the drogue parachute. And it was really exciting to see actually the timer go down and at the 0 seconds actually having the drogue rift, having everything working.
That's of course exciting always to see your design.
Exactly.
And then I have just one more question for you. Do you have any plans to stay in there for the next years, or what are your plans for the future?
Yes, so I'm planning to join Axolotl. This is basically a continuation almost of Stratos 5, as it will be the main leading liquid project. We will start with a smaller engine this time to actually learn perfectly the liquids and how their performance is and characterize them.
Okay. And what will you do within the team of Axolotl?
I still don't know, because we just started and I'm new to the team now, as I just left Stratos, as the project is ending, and I'm still helping with the team.
So a lot of unknowns.
Exactly.
Also exciting things to happen. Then I want to thank you for your time and for this interview.
Thank you.
Wish you luck.
Yep, thank you.
Hi, could you introduce yourself?
So my name is Przemysław Lesiczka, but in the team I'm known as Benny. I'm a member of Stratos 5 Electronics, and I've been part of electronics for the past 2 years.
Okay. And what did you work on in Stratos?
I've worked on almost every single part of the electronics in Stratos 5, but primarily I worked on the ground system. The ground system consists of the launch boxes, through which we give the final, through which we initialize the launch sequence of the rocket. I also worked on the ground boxes that are at the rocket, at the launch pad. These power the rocket, they provide communication between the rocket and the ground station. I've also developed a few PCBs myself. It's probably the most rewarding part of being in Stratos. I'm from an aerospace engineering background, and learning Altium and actually becoming good at electronics was the most difficult part of being in Stratos 5.
Okay, and can you tell me a bit more about the PCBs that you developed yourself? What do they do?
So I've worked on 2 PCBs mainly. I've worked on a communication PCB, which the main purpose of it is to detect the ignition of the rocket, but also facilitate communication between different communication protocols. So our ground systems work on a different communication protocol than the rocket does.
Great, interesting. And what was for you the biggest challenge this year? Of course, you kind of gave a little bit the answer already, but can you go in more detail? Was it the manufacturing itself, the testing, or?
I think definitely developing PCBs from scratch, where I had no background in this, and now I'm able to not only design PCBs but also
manufacture them, program them, and of course debug them. That's probably the most challenging aspect of being in Stratos. Also, just learning to work with the system itself. I've been to many hot fire campaigns where I would be working with a few people at the CP, where I actuate valves, I run various sequences, and getting thrown into a very challenging environment like that was also quite difficult because you're operating a quite dangerous system and you need to always be at the top of your game to really make sure that everything goes well.
Okay. And then I have a question about what the most rewarding single moment in this year was for you.
Definitely witnessing a hot fire for the first time was definitely the most rewarding experience of this year. It was a very rough day, being at the test facility the whole day, and the whole day you're just stressed, not knowing if you're gonna get to fire the engine, and then suddenly you fire it and it works. It's an amazing feeling.
I agree. Then I have one more question for you. Are you planning to stay in there, or what are you going to do in your next year?
I'm yet to decide. Of course, I've been in Stratos for 2 years now, and with Stratos ending, I might look for a different team in there, but maybe I might move on to something a bit more different or maybe a bit more complex.
Okay, then I wish you luck with whatever the future will entail, and thank you for your time.
Thank you.
Well, so as you can see, there are a lot of people that are working on Stratos 5.
In the backgrounds of the interviews that we have just seen. And so we are going to talk more about that.
Yeah. So they're right now. So in Portugal, they're also working on the rocket, and we do have a photo.
Of everyone putting the final touches on the rocket, getting it ready for the launch pad.
If we have a go from our... Yeah, it's on?
Yeah.
Okay. So one of the things you can see is actually an external line that is running around the LOX tank. So if you have the rocket, you have, of course, the engine, which is the closest to the camera right now. Then you have your LOX tank, and afterwards your ethanol tank. We first wanted to design the LOX tank in a way that we had the ethanol tank run through the LOX tank. Because
Like a donut of liquid oxygen.
Yeah, basically. But this is quite difficult considering that LOX is, well, extremely cold and your ethanol is not. So this could freeze up your pipes, so it had to be very much insulated. A workaround, a literal workaround, is to have the feed go around your LOX tank, which you can see in the picture. You can also see how it flows into the main valve, which is also visible. Yes.
So that's what the pipe you're seeing. And now we are seeing that we have gotten a question, which is that is there the projects, are they managed by the university? And the answer is no. Even though we are supported, and we'll talk more about that, of course, by the university, we are not actually managed by the university. There is a student team, so it works separately from the university. But our funding mostly comes from membership fees, but also our sponsors and the people, companies, institutions that support us. So with that, we will talk about our sponsors. There is a part of the Delft University of Technology, and we are proud to be a part of and represent our university. The continued support of the university allows us to pursue our mission of giving students hands-on rocketry experience. And we are grateful to the university for giving us the foundations, the facilities, and the academic environment needed to make awesome projects like this possible.
We would also like to thank Tej and Aramid for their continued support. They have been supporting us since Stratos 3, which, if you can count, has been a couple missions prior. They provided us high performance parachute material, and they were supporting the project overall. They have been a crucial role in the reliability and the success of our recovery systems. We truly value this long-standing partnership and look forward to continuing this incredible collaboration into the future.
Additionally, we would also like to thank 3D Systems for their support. They have been supporting us since Stratos 4, and their advanced additive manufacturing technology has allowed us to manufacture our engines, including the DLX-150C, which is on the current Stratos 5 that you will see launched today. And it was made out of the material Inconel 718. We are excited to continue to push boundaries of rocket engines and student rocketry with 3D Systems.
Then we also would like to thank Nippon Gases for their continued support since Project Sparrow. Nippon Gases have been providing us with the most essential gases and liquids, such as the liquid oxygen, helium, and nitrogen gas. And even now, during the EuRoC launch campaign, their support is still invaluable as they provided us with our liquid oxygen. Yeah, we deeply appreciate their continued partnership and trust in our mission.
Next, we would like to give our sincerest thanks to the 981 Squadron at Woensdrecht. They've given us their facilities and allowed us to use them for integrated testing, engine testing, and with that, they've allowed us to perform hot fires, which means the engine actually ignites, cold flows, where we test for leaks so the engine does not ignite, and most importantly, they've allowed us to maintain the highest degree of safety in all of our tests. Additionally, their assistance with manufacturing various components has been invaluable in making this rocket ready for today, for the launch. And we are sincerely hoping to develop and continue this collaboration with the 981 Squadron at Woensdrecht.
And then another one of our sponsors is Rominox. We would like to thank them for the continued support for Stratos 5 and Project Sparrow. They provide us with high quality valves, including very specialized cryogenic valves for our LOX flow. These are, of course, very essential for our system. Additionally, their tech support and expertise were very much crucial in the engineering of the rocket. Yeah, we would like them for helping us in our partnership, continued partnership and progress towards our mission right now. Yes.
Yes. So after thanking all our sponsors, we would like to show what they have actually helped us produce. So we will have a video about our mission.
Yeah.
My name's Luke Gamasmer, and this year I was the team manager for Stratos 5.
Chief of Structures.
Electronics Department.
I worked on recovery this year.
Chief of Propulsion.
Structures Department.
Project Stratos is a student initiative from the TU Delft, from a group called Delft Aerospace Rocket Engineering. The main goal really is to reuse a rocket. So we want to show students and industry that reusable rockets are achievable, they're feasible, and if they can be done by students, they need to be done by industry.
I am Jan Struzinski. This year I was chief engineer. There's a number of special things about Stratos 5. First of all, this is the first time we are going to launch a bipropellant liquid-powered rocket. All of our previous rockets, they had much simpler types of engines like solid propellant or hybrid propellant engines.
Explain me the difference between solid, hybrid and liquid propulsion.
Okay, so solid propulsion has a fuel grain which has oxidizer and fuel pre-mixed and then cast in a tube with a hole down the middle. And then you stack a couple of these grains and you burn it from the inside out. Liquid fueled engines have, well, a liquid fuel. Just inject the two, mix it, spark it, and then it burns. And then I get something that looks like this, comes out the hot end. With hybrids, you're, well, right in the center. That's why they call it a hybrid. You have a solid fuel, again, cast into a grain with a hole down the middle. And you inject an oxidizer from the top, and, well, that burns with the solid fuel. The advantage of a liquid-fueled engine over a hybrid engine is primarily efficiency. The fuels that you can use in these can push to way higher efficiencies, so you just get more oomph per kilogram of propellant, which, well, you really want in rockets because every gram counts.
Secondly, this is also the first time we'll recover almost like the rocket that's that big. It's 120 kilograms of dry mass, and the recovery system involved is quite cutting edge.
Hello, my name is Nachiket Dige, and last year I was in the recovery department of Stratos 5 as a part-timer. So recovery is really important in any launch vehicle. Recovery is a set of functions that determines how exactly a rocket is going to land safely back on the ground. So Stratos 5 has a very special place for recovery in itself. It's going to be one of the first rockets of the main flagship Strate that is going to be fully recovered.
So compared to earlier rockets, we want to recover the entire thing. So that means you need to have basically bigger of everything, which makes it harder, but also the package things inside of the rocket becomes more complicated. Diameter will be roughly 5 meters.
So we have a really special initial decelerator called a balut. A balut is a hybrid between a parachute and a balloon.
These are our main parachutes. These are some examples, but the one we hope to at least fly in Stratos 5 is actually going to look a little bit like this. It's got a lot of little bits of cloth. These are called ring sails because they're just multiple rings of sails. And I think a ring sail, at least in the past, if you've seen Apollo missions as well, they've opted for ring sails for, well, its drag efficiency. So that's why we've opted to use them instead of, say, previous designs such as in Stratos 4 or Stratos 3.
So one of my favorite moments of last year was manufacturing our balut with the rest of the recovery team. It's always nice to see what you have designed and analyzed for such a long period of time come to life.
So there's a lot of novel technologies involved. And I think what's special about this project is that it takes these different technologies, different teams in there were working on throughout the years, and then it combines them together into one project and one system.
We are a team of full-time engineers, so people who dedicate themselves for the entire year, 9 to 5, maybe even more. And we're a team of even larger part-time engineers. We're in total like 80 engineers right now. So it's a massive team.
Successful team pictures, right?
right?
Yes,
Consulting.
successful.
Nice.
The start of the documentary.
Start of documentary.
And so at the beginning of the year, I was really anxious. I was afraid that I'm gonna waste the potential of my engineers, because the role of chief of structures, chief of the department, was new to me. That of course has changed over time. Now I feel more comfortable managing the team. I feel more comfortable working with certain systems within the rocket, of course. I feel accomplished in that sense that I created a team that can design pretty much any structural component.
Okay, so this is the thrust structure we built this year, and yeah, as you can see, it has been tested and all of the beams are quite bent. But yeah, this was, I guess, the main achievement of myself this year, that we had a big production crew who manufactured this and then tested it in the aircraft hall. The moment that I will remember for a long time is the compression test of the thrust structure, because I started working on it like during the winter period, and then I iterated on the design a lot of times, and finally we got to manufacture it and see it work during the test.
The moment or the experience that will forever stay with me is going to Bremen for the Space Tech Expo. With us, we wanted to take Stratos 4, and I was responsible for actually assembling the rocket after laying for 2 years in the basement. It's a challenge to actually find all the components, assemble the rocket here on campus, and then transport it to Bremen.
Hello. So my name is Kubra, and I worked as a part-timer at the structure department. I think one thing I achieved was, first of all, work with different type of people, because I'm doing the master's. I was at one hand involved with a bachelor. Another thing is you have to convince companies in order to build something for you. So you have to come up with a good speech, explain to them what you did in the design and so on. So I think that was also quite interesting experience. One of the things that is really memorable to me, it's maybe not very directly connected to the technicalities, but once we had like a meeting with Airborne in their facility, and we had a nice talk. Like, we presented everything we had, and they were on board on helping us with manufacturing the IVS. And on our way back to the faculty, we dropped by the IKEA, took like a lot of hot dogs and brought that back to the team, and that was like one thing that I wouldn't forget easily. So I have to really think about my favorite machine, because there are a lot of machines I really like. Maybe the tensile bench, that's a nice machine.
A unique project to me is the people that I'm working with. As I said, I had the chance to work with very knowledgeable, amazing people, and I think we can always design a hardware for a group of engineers, but designing a hardware and having fun on the way, that's something new, honestly. Oh man, I love all aluminum alloys, but my favorite one, I think, would be aluminum copper one, 2219. It's aluminum alloys frequently used in space missions. It has excellent mechanical properties. It works fantastically in cryogenic environments. And lastly, and most importantly, it's easily weldable.
You had this planned out.
For me, the biggest challenge I faced this year was definitely going into a role that I had no experience in. At the beginning of the year, I think we were all quite scared. We didn't know much. It was a new project. We had to transition from a technology development project all the way to a full rocket development project. Develop a lot of methods or kind of tools to successfully get this project off the ground. What's amazing is that you take this break in your studies and you get to do this full time for a year. And like, the recipe to a successful skill is just practice. And so when you're spending 24 hours a day, maybe not, you know, we don't work that intensely, but we work hard at what we do. And when you consistently do that for a whole year, by the end of it, you're really experts in what you do.
The proudest moment of this year was when we hot fired our engine. Looks like this. It's not this exact one. The nice one's strapped away in a box, but seeing that thing come to life again was a very nice moment.
Favorite moment? That's really tough. I think the first hot fire we did, since I was allowed to press the button, it was really exciting and I was really nervous for it. But it was really cool afterwards when everything went successfully. It was amazing, the feeling.
A moment that'll forever stay with me. Probably long nights before testing and the tests themselves afterwards, particularly the hot fires. Those are the amount of work that you put into it, and then the payoff, even though it's 2 or 7 seconds long, it's totally worth it. It's great.
Rocketry is an industry it's very exclusive. Not much is known about it. I mean, it's really hard to get into, and so if you already have engineers that have had experience building rockets for 3 years, they're going to come quickly into your company and they're going to be the leaders of the next big company. They're going to be the next big engineers. They're going to really revolutionize the space. And I really can't wait to see what my colleagues and my teammates all get up to in 5 years, because I reckon you're going to see them at a lot of big companies, and they're going to be working on the next big thing. So Stratos 5 has 2 more years left, and come the summer of 2025, this rocket will launch, and I can't wait to see it. And I want to encourage everybody on the team, let's do this. Let's make this rocket a reality. Let's finish what we've started, and I can't wait to see this thing fly.
Well, as you can see, that was quite an outdated video because some of our requirements have evolved over time as the mission and project has been going through into the future.
But most of what was in the video is still applicable, so you can still get an overarching picture of what we are going to be launching today by watching that video. And now we're going to segue into some more interviews.
Yes.
You can say more about it.
Yeah, I think we're going into structures. Sorry?
So first we will start with the structures interviews with Boas. So if you can cut to that.
Well, hi. Can you introduce yourself and your role this year in Stratos?
Well, I am Boas, and I am part of the simulations department of Stratos 5. We run the simulations on the rocket, and depending on the simulations, parts of the design also do change. Yeah, In the latter half of the year, I've also done a lot of other things besides simulations, like machining and actually constructing the rocket.
And what kind of things did you machine for the rocket?
I made the tank flanges, and this is like kind of the caps on top of the tanks, and I also made the helium manifold, which is like the first piece of the feed system after the helium tank.
Okay. And to get back to simulations, what does simulations especially do for the Stratos 5 launch?
Well, the goal of simulations is actually to make the launch as safe as possible. We want to find out where the rocket is going to impact the ground, and preferably want that to be in a spot that is not occupied by people. And that is what simulations is for mostly. And on top of that, simulations is also for gauging the performance of the rocket we are building, which mattered in the first half of the year.
Yeah. And when do we do the simulations? Is that the day before or in the morning?
Well, for the actual launch,
yes,
we'll probably do the simulations with the most accurate weather data we can get, like as close as possible to the launch. And during the rest of the year, we've also been doing simulations. Simulations like not the thing you do only once, it's the thing you do throughout the year to test your rocket and to gauge the safety.
And are there also, for example, design changes that happened because of simulations that we made?
I need to think a little bit. I mean, we definitely decided on the burn time using our simulations. The burn time kind of decides how high we go, and at first we still wanted to go to 9 kilometers at EuRoC, and then we needed a burn time of 8 seconds, which we calculated in simulations.
Okay.
And now we decided on 3 kilometers, which needs like a burn time of about 3 seconds.
Okay. And what was the most exciting or rewarding moment for you this year?
I think up until now it has definitely been literally the last day of my summer vacation when I was at the test cell, and we somehow managed to hot fire our kind of integrated system for the first time.
What made this so special?
Well, like a lot of emotion went into it, especially because of the previous 2 days in which we had 2 failures for hot fires, like not catastrophic failures, but they didn't work out. And of course, I put in a lot of work as well myself. Like as I said, I machined several parts that were actually being used in there for their intended purpose this time around. And I also was doing quite a lot of stuff around the campaign. I helped with box cleaning, I helped with sampling. So yeah, it's just kind of a combination of everything you've done up until that point. And if it works, that's a good feeling.
Yeah, of course. Sounds logical. And then I have one more question for you. Do you plan to stay in there or go into industry, or what are your plans for the future after Stratos?
Well, short term, finish my masters and I'll be staying in there. I actually already joined another team officially, but I haven't really started work on that yet, as the focus is going to be on Stratos 5. But apart from finishing my studies and staying in there while doing so, I don't really have plans for the future.
Okay. Well, I have to thank you for taking your time to do this interview, and good luck at the launch pad.
So after that piece of information about structures from simulations chief boss, we have our one final last interview from the chief of Stratos, which is Danny.
Hi, could you introduce yourself?
Yes, hi, I'm Danny, the Chief Engineer and Project Manager of Stratos 5 this year.
And being Chief Engineer of Stratos 5, what does it specifically entail?
Well, in general, that means that you are the lead on the technical side of the project. I supervise and check the engineers' work, who builds the rocket and design each component. This means that I have to check technical drawings, or just in general assembly designs, etc., etc., or just in general help out wherever I can, whichever department or rocket section needs some extra help.
And speaking about these departments, how did you make sure that the departments themselves worked together?
Well, so of course this is a cryogenic biliquid rocket, which is by its essence quite a complex technology and quite a complex system to work with. So of course you need to employ some system engineering practices. Of course the project itself is not that big, or at least it's not comparable to, for example, the NASA or SpaceX project. However, it still requires cooperation and collaboration on certain rocket sections, certain departments, certain areas. Of course, you can build a feed system and an engine for a rocket, but if you don't have the electronics integrated properly, you won't be able to actuate any of the valves. And of course, if you don't do a structure, if you don't build the rocket itself, then well, your engine will never actually fly in the rocket. So it's very important for all the departments to do their work and work together to make and build the rocket. But how did we do this in practice? So the team is overall not too big, and we worked mostly full time on it in the past year, which means we've been stuck together in the same room or same workplace for the past year, which means we can communicate very easily about the department's needs and requirements towards the other departments, which makes it quite easy. Of course, we also employed the use of Polyspace, which is also a system engineering platform, or just in general a simple Excel sheet. Sometimes when it was easier to just use that to basically communicate our needs between the departments. We also had several meetings, usually once every week, to discuss the progress on the rocket and see where we need to work more together. For example, during the integration phase of the rocket, we had several meetings where it was only for the relevant people, and only the relevant section or assembly of the rocket was discussed. For example, the recovery bay, or the instrumentation bay, or just the tanks themselves.
And of course, that everything works together has to be tested, right? How did we manage to do that? And what was your role in that?
Yes, so in general, if you are lucky enough, you get to test every component of your system before flight. Of course, sometimes, especially with time limit and with a smaller budget and resources like us, it's not always possible to test everything to perfection as you would want. But until they work just fine enough, it's okay. And of course, we always test at least the most crucial and safety critical components of the system, which we did. But what was my role in those? In general, I am the one who organizes these testing campaigns or just testing days. If it's a smaller testing that needs to be done. During those testings, I usually just supervise the engineers, see that everyone does their work properly. And of course, I am also responsible for the logistics of the campaign. Sometimes we don't have a lot of people available for a day, for example, then I also always pitch in and help wherever it's needed to build the assembly or to work on the system during the tests.
Okay. And for example, on bigger campaigns, what did we especially test in those campaigns?
Well, we basically had bigger campaigns for the propulsion and the electronics of the rocket. We go to a military base in the Netherlands where we can test this engine. It's since it's quite a big and powerful engine, the record for us that we hit with it was 11.5 kilonewtons roughly. So of course it requires a secluded and safe location to do this test. That's why we tested the military facility. But what do we do there? We assembled the setup. For most of the year it was like just a ground testing bench. But for the final campaigns, we tested the full rocket assembled together as it will fly. The campaigns were quite hard. You need to do a lot. They are very busy days that last from 7 in the morning until midnight if there is something we need to fix in the evening, which usually is the case. So it's quite a tiring thing, but we managed to pull through every single one of them so far. So that's all that really matters, I guess.
The result matters. Yes. And well, talking about results, what was the most exciting thing that happened this year with Stratos? So far, of course.
The most exciting thing. Well, quite honestly, I guess the most exciting thing that happened was the fact that we have a rocket, or that we had a rocket reveal. It's been quite. Last year has been quite a slow year overall for the project, but thankfully this year things have been a bit faster, and we could actually manage to build a rocket. We kind of employed a bit different approach to the project than our predecessors. We kind of stopped designing everything to perfection, and we just started testing and building stuff and seeing if it works, and if it's not, we just iterated on it. And this way we managed to do everything in a way faster approach. Of course, the rocket is not perfect, but that's also not the point of the rocket.
If it works, it works.
Exactly.
Right. And talking about the rocket, are there any payloads on the rocket?
Yes, there are. Actually, there are two of them. One of them is a VI-Tech PR ducky. It's a small rubber ducky. Of course, it doesn't have any big function during its flight. It's mostly just to showcase that rockets, and especially student rockets in need of sponsorship, can also use their rockets as a launch vehicle for PR and sponsorship payloads as well. Other than that, of course, we also have a scientific payload, as in general that's the biggest use of launch vehicles. We have a muon detector on board. It basically detects muons in the atmosphere, and the whole reason we want to detect muons in the atmosphere and count them is because there is this hypothesis that we want to prove again, that muons degrade in the atmosphere basically the closer to the ground you get. And that's something that we can test with, basically counting the muons over the flight profile of the rocket. But of course we didn't make this payload. This is a payload that was made by a group of students from Leidse Instrumentenbouw School. It's like a technical college It's a bit different from a university. It's basically a bit more hands-on experience. You learn how to machine components, metal components. You learn how to use a CNC. You learn how to do glasswork, stuff like this.
Alright. And then I have just one more question for you left. What will you do after Stratos?
What will I do after Stratos? Well, I will definitely take a little break after this long year. But I also have other plans coming on. Of course, in there, Stratos 5 is not the only project. There are many other projects ranging from other bi-liquid rockets to space shot solid rockets, and in one of the projects that I'm going to be helping out next year, which is Chimera. It's a hybrid rocket project. We are going to design a new engine, most probably with liquid oxygen as the oxidizer part of the hybrid.
Sounds like great fun. Then
hopefully it will be, yes.
Yeah. Then I want to wish you a lot of luck during the launch campaign on the test.
Thank you very much.
In EuRoC. And
let's hope for the best. Yes.
Well, thank you for your time and.
Thank you very much, guys.
So that was a wonderful interview from Chief of Stratos, Dani. And with him, you can also see our amazing bus called Buster. Buster is our vehicle that we use to transport the rocket from our faculty, the aircraft hall where it is kept, to the launch sites, wherever they are, in the Netherlands, in EuRoC, wherever they may be. And also, it is very important as our getaway vehicle for people going to the launch pad, arming the rocket, and then going away from it as fast as possible before it launches.
Yeah.
But I see that we have gotten some news about EuRoC. The launches that were going to happen at 2 o'clock have been postponed to 4, so they are going to share the launch window with Stratos. So stay tuned to hear more about what happens with them as well. It might cause some delays with when we are going to launch Stratos, but we have not heard anything about that yet. Until then...
Yeah, so in the meantime, we're just gonna look at more Hotfire videos because they're just cool. We're gonna look through the first test, so the one Sparrow did, up until the last integrated Hotfire, which we've done this August. So yeah, let's see. Well, those were very interesting videos. Some of these were also included from the last hot fires, the last ones to be specific. Um, yeah, I'm now gonna talk a bit more about what we actually did during the tests. So, what a usual hot fire test campaign would look like is, of course, we'd have all the prep, so making sure all the stuff is at the aircraft hall and that that's all checked off, it's all in place. And then usually we would head off um, in the evening before we start, and we would drive to Woensdrecht and then sleep on the military base, which is very interesting. Um, Afterwards, during the test, we would, of course, first set up the entire system, make sure all the valves are connected, all the pipelines, and all the electronics. Afterwards,
And
we
also all kinds of monitoring systems to make sure that if there's some problem with the locks, the valves, anything like that, that we are able to realize that immediately before it becomes dangerous.
yes. Um, so then for what we first do is we pressurize the system. So we bring out usually a nitrogen gas bundle because nitrogen is a bit cheaper than helium. And we pressurize the system. We do this in increments. And then we test every fitting, every valve, see if they're leak tight or not. And of course, we want them all to be leak tight. Afterwards, we start filling the ethanol side and we do a cold flow on the ethanol side to make sure that the ethanol goes through the system like we intended to. Then we do the LOX filling, which is we need to pre-chill. We need to make sure that the system can handle the cold temperatures.
So pre-chilling means that if you have a room temperature engine and then you put a whole bunch of LOX in it directly, because LOX is like really cold, then it's going to cause a lot of thermal stress on the metal of the engine. So because of that, we release a small quantity of LOX first to chill the engine, which we call pre-chilling. And only then do we release the amount of LOX we expect during an actual ignition test.
Yes. And then after the cold flows have been performed and they're all done successfully, we do our hot fire, which, as you can see, we have done successfully many times.
Yeah, so a cold flow is where the propellant, so the ethanol and the LOX, are released into the combustion chamber of the engine, but they don't actually ignite. They just come out of the engine and are disposed of safely, of course. Because, yeah, LOX is dangerous. It's cold and extremely flammable. And what ignition test is where the combustion chamber, we actually ignite the LOX and the ethanol so that we can check that that goes smoothly as well. So both tests are important.
Yeah, I think we also want to talk a bit about the payload.
So the Stratos rocket is going to carry a muon detector as its payload. The point is that muons don't make it through all the way through the atmosphere. So to check the gradient of how many muons there are, or like the muon concentrations at altitude, you need to send the muon detector to different altitudes. For that, we are going to use our rocket. And with that, we would like to segue into some of the other teams that are part of there. For example, would you like to talk about Chimera?
Well, Chimera is very interesting because we are doing hybrid, which requires a solid fuel, but we will also use LOX, and a lot of the Stratos 5 teammates will actually continue their work within Chimera. We are right now designing the engine, so nothing has been done yet, but yeah, we're very interested into kind of keeping this technology, especially for the LOX, still within there without it like fading into the background and obscurity. So yeah, that's Chimera. I don't know if you want to talk about any of the other.
Yeah, one of the teams that was a part of Stratos but now kind of branched out into its own teams is Turbo Machinery. So when the original goal of Stratos was to go up to 50 kilometers, the modeling had predicted that we would need a turbo pump to go with the engine. But now that the goal of Stratos is to go 3 kilometers, it doesn't need it anymore. And putting it one on would add increased complexity and unnecessary weight. So we've decided to just split that team off of Stratos. So now Stratos, the rocket, will launch without the turbo pump. And the process of trying to develop and design a turbo pump that goes with the Sparrow engine that Stratos uses is now part of a different team. So the hope is that we are going to be able to reuse the engine of Stratos once it finishes launching, because as you have heard in the mission video, that was one of our goals for Stratos, to make it a reusable rocket. Then we are going to use that engine and see if our turbopump can attach with it. So that's going to be a separate test that will happen hopefully later this year.
Yeah.
Any other teams you would like to talk about?
Well, if I do want to mention, maybe Quetzalcoatl, it's a small team of ours, a couple friends of mine. Yeah, we're hopefully launching at the ASCA, where usually other rockets also launch within there. And we're going to be trying to test air braking, which has not been done successfully. Of course, there's a lot of safety factors we have to take into considerations, and these will also be discussed with the safety. Yeah, with safety, because we don't want anybody to accidentally have a rocket on their head because one of the air brakes fails. But yeah, that's like a little bit of a shout out to Quetzi.
Yes. A similar goal to Quetzi is also for Haystack this year, where we are trying to build a rocket that beats the ASCA, which is a military base where we launch, the speed record at ASCA. The main thing with this is that because we have a military mandated 2.5 kilometer height limit, it is important that we are able to stay under this limit and still achieve the speeds that we are hoping for. That means that not only do we need a fast rocket, we need a rocket with high acceleration, and then quickly decelerate so that it also keeps within the time limit. And so for this goal, we are trying to find innovative strategies such as a two-stage rocket, for example. So that is the other team where I will be also working on electronics after Stratos launches, and I will have not more electronics work for Stratos.
I think we want to show some videos again of the recovery system, the test, right? And then segue into some explanation about these tests.
Yes. So we will go through again the tests on the parachutes, the drogue, and the main parachute, and then we will talk more about it again.
Ribbons.
Copy that, I'm good to go.
It's a design choice.
Yeah. Copy that, going to 20 starting now.
Actually, let's add drive.
How big is that
Can it be
ribbon?
quiet again in the room, please? Because we're gonna go to 20, which might
second. That's fine.
Can we go higher? Is there not there anymore?
Oh shit.
Yeah. Okay. Okay.
Looks pretty good. Yeah, I think it's already touching.
It's very stable as well.
That's not the problem.
Oh yeah, but the load that it's pulling.
It's kind of small. Like the between the reefing lines.
Well, so this is Dan, who was our behind the camera guy, but now is going to tell us about the parachutes that you just saw. So Dan, tell them things.
So it's actually quite interesting. As we've told you before, this is an extremely large parachute. It's actually so large that you can fit two people laying on it after each other and still have room to spare. It's quite funny because when something is that large, it's really, really hard to fold, as you can imagine, especially this kind of shape of parachute. As you could see in the previous video, the very large one, the main parachute, it has a lot of tiny rectangles. And to actually fold it, you have to perfectly get those rectangles on top of each other so that they fit nicely and you can roll it up very nicely. Because as you can imagine, you can't just stuff a parachute into the rocket and imagine it will deploy. You have to fold it in such a way that if it falls out on its own, it will deploy on its own and catch the wind that way, which is really quite difficult with such a big parachute.
So how did you do it?
So that's actually thanks mostly to one of our teammates in recovery, Nico. He's an experienced skydiver and has dealt with these kinds of parachutes before a lot because they are used a lot in that. So he knew how to fold it. What you basically do is you just fold it first in one direction, and you use the Z folds, which are a special kind of fold that makes sure that if uh, pressure is released from it, it deploys on its own. That's mainly it about the folding. Yeah. So a lot of the tests we did in recovery that I personally was part of are not actually shown on this live stream because we have footage of them, but it's not high quality footage, as you can probably imagine. Um, a lot of these tests were regarding to how the nose cone deploys. Um, this is done using pressure. So what is the case is that we have these cold gas devices that deploy canister of CO2, one that you would regularly see for pumping up bike tires or for life vests or stuff like that. When these gets punctured, they release a lot of gas, which expands very, very quickly. After this expands, the nose cone will shoot off, which allows our deployment. So we've done a test of that in the wind tunnel successfully, which was very exciting.
So does the nose cone like just come off? Or does it stay attached?
The nose cone shoots off. So you want a certain amount of relative velocity of the nose cone to the rocket, as you can imagine.
Yeah.
Because during apogee, the rocket will not be stationary. Yes, it will not have any vertical velocity, but it will have quite a lot of horizontal velocity.
Okay.
So we assumed to be, I believe, 60 meters per second of horizontal velocity, which, if you don't know how much that is in kilometers an hour, that's around 240 kilometers an hour.
It's like faster than a train.
Yes, it is twice as fast as the highway speeds in the Netherlands. So to make sure that the parachute actually inflates and the nose cone pops off, you have to have quite a lot of relative velocity of the nose cone to the rocket. That way, also, when it pops off, you will immediately be pulling it tight, the parachute. That way, it's easy for it to just inflate on its own. Of course, if it doesn't get pulled tight, it still inflates. It just takes longer, which is suboptimal
Okay.
to reach higher velocities.
So our wind tunnel at the Open Jet facility in TU Delft is not big enough for the 5-meter diameter, right? So how did we manage that?
So what we did is we used a method called reefing. What you do is you basically tie a line around the entrance of the parachute, that way cutting off a lot of the airflow into it. This means that the force it generates is a lot lower, and also, of course, its diameter is small. The full 5 meters would quite literally not fit in the building, not just not in the wind tunnel, but not in the building. So that's really, we had to refit an extreme amount, a reduction of more than 50% of entrance diameter, which, because it scales quadratically, is a lot of force that you lose from it. So that actually allowed us to also be able to use the test bench we regularly use for these kind of tests, because if we didn't do that, it would quite literally be ripped out.
So it's more safer this way, right? To use reefing for it.
It's not only more safer, it's actually the only possible way we could have done it.
Okay.
On the rocket itself, the parachute will also be reefed, but only for a short amount of time. So after we reach around a couple 100 meters of altitude, we will unreef the main parachute using the reefing box that was talked about by Federico earlier in an interview. I just got updates from our EuRoC people. It seems that Stratos will not be launching today.
Because there is no liquid oxygen availability at this moment.
Very, very unfortunate. Quite sad indeed, but nothing we can do about it.
But it's okay because this is not the last launch window of this campaign, so it's possible that we might be able to launch tomorrow or on Tuesday. So for today, we will be doing some small tests so that we can be more prepared for tomorrow and the other launches. Okay, so the latest news is that the launch will probably happen tomorrow. So today will be the testing for preparing for launching tomorrow.
Yes. We will now be cutting to the live stream, so thank you for watching.
we have Nathan back again to give us the updates from EuRoC to see what happened.
So, Dan was explaining about the recovery system. We just got an update that they didn't have any more locks. If I am correct, this is due to the dewar that was given was a hospital dewar, which had different settings for its venting, meaning that some of the lock leaked out, so to speak, vented out overnight.
Which means that there was less locks in the dewar than there should have been.
Yeah, so they're doing a couple of more small tests, probably making sure the system still works electronics-wise, valve-wise, but nothing else today. Tomorrow, we are not sure which launch window they'll be doing, but they're gonna try to launch tomorrow. Yeah, we would like to thank you for watching today. And,
yeah, and tune in tomorrow. Hopefully we will actually launch. So until then, bye-bye.
Bye-bye.